Welcome back to Calculus 2, section 8.3, infinite series. Definition. Series is the sum of the sequence. Technically, you replace your commas with plus signs, you add it up. Notation for the series would be sigma an, where this n starts, let's say, at 0 or at 1 or at 5, and could go to some finite value m for finite sequence, series, or to infinity for infinite series. Now, we do not study finite series because those are always convergent. Let's say you have 5 terms to add. They will add to a finite value. You have 10,000 terms, 150,000 terms. It doesn't really matter. If you have a finite amount of terms, they will always add to a number. Therefore, those always converge to a value, and there is nothing to study there. However, infinite series that add all of the terms all the way up to infinity are the ones that are interesting, because those could converge or diverge. Again, divergent means adds up to positive or negative infinity, and converge means that it adds to a finite value. We are going to learn 10 different tests to test these series, because let's face it, we're not elves to sit there forever and add numbers forever. So let's find a faster way of figuring these things out. I will first explain what it means for the series to converge to a sum. And then we are going to take a look at the first 2 tests that are in section 8.3. And then next section introduces 3 tests. The following section 3, and the last one introduces 1. No, it goes 2, 3, 4, 1. Yeah, 2, 3, 4, 1 for a total of 10. So if I have an to be a sequence, let's say 2n plus 3, we know that we can write that sequence as, and let's say we start at n equals 0. So we can start at 3, and then next one is 5, and then 7, and then 9, 11, 13, and it will go forever. So these are the values that we would encounter. Now, you notice the 3 dots at the end, which means goes forever. If I'm to look at the series of an, starting at 0 going to infinity, we are going to actually look at the series of 2n plus 3 from 0 to infinity. And what we get is 3 plus 5 plus 7 plus 9 plus 11 plus 13 plus, and that's going to go forever. It shouldn't take too much brain power to figure out that this will actually add to infinity and that this will converge. But how do we actually show that? Well, we study the sequence of partial sums. we can look into the sequence of partial sums. So what is the sequence of partial sums? Well, S0 is going to have only 3 in it. S1 will be 3 plus 5, which gives us 8. S2 would be 3 plus 5 plus 7, which would give us 15. S3, 3 plus 5 plus 7 plus 9, which gives us 24. I'll do one more. I'm already tired. For the sum of 35, and you can continue with this forever. Now we obtain a sequence of partial sums which is given as 3, 8, 15, 24, 35, and goes on forever, which clearly diverges. It is unbounded, monotonic, increasing. It must diverge. Since the sequence of partial sums diverges, the sum must diverge for the series, which is the series. No, add to infinity diverges. Converges if you add to a finite value, like 1/2 or pi over 2 or 7. Yes.
You said the sequence of partial sums diverges, so what else diverges?
Series from where it came from diverges. So if we have infinite series, it can converge or diverge, and we can always look at the sequence of partial sums to determine whether the series will converge or diverge. We are going to, well, we are not going to use this method. So we are going to take a look at 2 tests that will tell us this, because we don't want to try adding all the numbers to infinity one by one, right? And then we definitely don't want to do partial sums, because you would have to actually do it for a long time, right? Much longer than what I have over there, to determine for certain cases and certain problems what it converges to, if it converges. So what we did is, what mathematicians did, and what I learned at some point, is devised a series of tests, 10 tests in particular, which you will memorize how they look like and when to apply them, and just apply those. The entire chapter, I already said this, is just based on taking limits over and over and over again, so you'll be much better experts in taking limits because of this section than actually section 2 where you learned limits. Because this is, every problem has a limit, you'll see that. We will start with geometric series. And we immediately look at the definition which is actually the test. So if series a arc to the k, where k starts at 0 and goes to infinity, is a series, right, with a being different than 0. And k starting at 0. And I'm going to underline that. Then summation ir to the k from 0 to infinity converges if r is in between -1 and 1, and diverges if r is less equal than -1 or greater equal than 1. And they also give the graph of this, saying that this is where the convergence happens and this is where divergence happens. Now this is exactly what you're memorizing. You're memorizing how the shape of the series looks like, and then you're memorizing conditions under which it converges or diverges. And this is the advice for the section, for the whole section, and then the next one as well, chapter actually. If you memorize these verbatim and you are able to shovel some basic algebra, this section is going to be a joke. If you try to make up mathematics for this and try to use way too much common sense, it's going to be a living nightmare. It's very simple because you haven't done stuff like this. This is not integration that builds up on precalculus, that builds up on derivatives, that builds up on algebra that you're used to. This is now discrete mathematics. We do not have functions, continuity, and stuff that you're used to. These are discrete points that are adding. And the only way to do this properly is to memorize these things. And I will tell you that as a student, I pretty much went through chapter 8 going, what the hell is going on? All right? And I did not learn it this way in terms of just memorize this and you'll be fine. It was let's try to figure out how these things actually work, and no. Memorize the tests, memorize how they look like. So here are the example. Oh, hold on. Very important thing. If it converges, sum is given by the formula A1 minus R over 1 minus R. Obviously, divergence goes to infinity. So this is your sum. Let's take a look at the examples. It will be much clearer when we have examples. First example says 4 times 1/3 to the k from 0 to infinity. Does this converge or diverge? Converge. Why? It's a very simple answer. R is equal to 1/3, which is less than 1 and more than -1. Therefore, it's in our convergent interval, therefore converges by geometric series test. And here is your R. It was exactly that 1/3. Actually, I'm going to put that formula on the board. Yep. If you memorize this statement, you just use your eyes and you look at the value of R and you know, convergent to divergent. You cannot come up with this stuff. You must memorize it. That's it. That's the bottom line. So if R I know, yeah. You gotta look at stuff now. So if R is between -1 and 1, we have convergence. If R is bigger than 1 or less equal to -1, we have divergence. You are memorizing this. So there is no calculation here, there is no computations, no procedures, no process, nothing. You look at this and you say A is 4, R is 1/3, 1/3 is in between these two numbers, the outcome is this. And now we can go ahead and compute the sum because we know it converges. That means if it converges, it has that one number that all of these infinity of terms add to. And that number is computed in the formula A over 1 minus R. So now we can compute the sum. S equals A over 1 minus R, which is 4 over 1 minus 1/3, which is 4 over 2/3, which is 12 over 2, which is 6. If I did this arithmetic correctly, all of the infinity of terms here will add to 6. Now you can go and write out this sum. You can do that because when k is equal to 0, this thing is 1. So the first term in your sum is 4 plus. Then when k is equal to 1, it becomes 1/3. 1/3 times 4 is 4/3. Plus, next term, k is 2, this is 1 over 9, times 4, 4 over 9. Plus, when k is 3, 1 over 27 times 4, 4 over 27. You can keep going and writing as many of these as you want. You have infinitely many of them.
Because they keep getting smaller.
Yes. So what this proof over here shows is that when you take this particular sum, write it out with all these pluses, it will add to 6. All of those numbers to infinity. Which is actually fascinating, right? Because you will be adding forever and ever and ever, right? But it adds to a finite value. To me, that's fascinating. I don't know about you. Is it?
It's fascinating.
There we go. You don't go today. Nice. Pure. Is she okay? Is she? Sure. Yeah. Next example. Yes.
So it doesn't work if k doesn't start at 0?
It does work, but you have to shift it to 0 to find the exact values. You can start k at any value. R can never change. R is the carrier whether it converges or diverges. However, the sum formula works in this shape and form only if k starts at 0. So if k starts at any other value, you will have to do something called shifting the counter, which we are going to do here. And you will technically reset that back to 0, and then you will be able to find the appropriate sum. So it will, if the k is not 0 in the original formula, which means right here, if that's not a 0, you will still get converges and diverges right, but you will get the wrong sum because it's not 0. Tanya? We know that if it's divergent, it adds to infinity. There is no need to do anything else. Divergent means all of the terms are adding to infinity. Look. Let's take a look at summation of 2 to the k from 0 to infinity. Converge or diverge? Diverge. R is equal to 2, which is larger than 1, implies diverges by geometric series test. You have to get used to writing this because we are going to learn 10 tests. And on the exam, you have a whole bunch of these scattered on a page, and you solve one and you say diverges by integral test, converges by limit comparison test, diverges by divergence test. So you have to state your answer is not just D, your answer is this, the entire thing. Casual.
Do you know that 2 wasn't A and R was 1?
I'm sorry?
Do you know 2 wasn't A and R was 1?
K is on 2. I can put in 1 times, so A must be 1 in this case. But I cannot fit 1 after the 2 because that will be inserting multiplication, and we know by order of operations exponents first, right? So there's no way to insert 1 there. All right, summation of 3 times 5 to the negative k from 0 to infinity. I'm sorry? Why? How? Yes. It's negative k. Because it's negative k, we have the algebra kick in first. We know from algebra that x to the minus 1 is 1 over x. So we get to rewrite this problem as 3 times 1 over 5 to the k. R is 1 over 5, which is less than 1, converges by geometric series test. You can go find some as well. Here. Let's do it one more time. Whatever is shortened, yeah. Yeah. Well, you will print it. One more. No coffee. Converge or diverge? Converge or diverge? Converge. That's it. Converges. R is 1/2, less than 1, converges by geometric test. And now you want to do the sum.
Oh, okay. So you have to. So that's whether it's converging or diverging. You don't need to
You just look at the R. Do we all see it? So, you have to memorize that the original test for which all the formulas work starts at 0. This particular problem starts at 2. Therefore, we will have to shift the counter. And you shift the counter to 0. All right, here is the procedure. We have summation of 3 times 1/2 to the k, where your k starts at 2 and goes to infinity. What I need to do is to make this 0. Therefore, common sense, subtract 2 on both sides. You have equation k equals to 2, subtract 2 on both sides to get it to equal to 0. So now it turns into k minus 2 is equal to 0. Awesome. But you really don't like that k minus 2 down there, so you are going to rename that one to n. So you are technically writing a substitution that n is equal to k minus 2. You don't get to memorize this formula. You don't get to memorize n is equal to k minus 2, because what are you going to do if this is 3 or 7, right? That formula depends on what number you start with. So if this is 5, then you will be subtracting 5 on both sides, and then it will be n equals k minus 5. So you don't get to memorize that thing, you just get to understand how to get it and then use it. But now that I renamed my counter from k to n, I have to rename the exponent as well from k to n. Remember the u sub? You change all x's into u's, and then you change also dx into du, right? So this is technically the substitution part, where you exchange all k's into n's. Don't forget to change that one as well in the exponent. So now from here, I know that k is equal to n plus 2. So now, n equals to 0 to infinity, 3, 1/2, and exponent is n plus 2. Awesome. We were successful in shifting the counter from 2 to 0. But we messed up the exponent, right? Right? Luckily we can fix that, right? Easily. Because it's plus 2, so just peel off 2 1/2, right? 1/2 squared. Peel that off, and we are using now the algebra formula, which says that x to the m times x to the n is equal to x to the m plus n. We're using it backwards, technically, because we have this side as n plus 2. So I'm going to separate this and 1/2 squared is a quarter, and I hope you see what happened here. Because the counter did not start at 0, your A was not correct in the beginning. That's the trick. So A changed in the formula. And you know that for the summation formula, A sits on top, and it's counted. So summation formula is A over 1 minus R. You cannot change R with this procedure, but A changed. We started the problem with A equal to 3, but because the counter was actually 2, not 0, starting at 2, when you go through this shift the counter procedure, you get your true A, the one that needs to go here in the formula. So now you know A is 3/4, R is a half, and you can find the answer, sum is 3/2. So now you can compute the sum, because we know that A is 3/4. And the sum is 3/2. Chapter 3 in differential equations. Section 3.2. I think everyone in this room has to take that class probably under the computer science guys. So, see that? That's that. Shifting the counter. Every time when you take a derivative of a power series, which is our chapter 9, so in differential equations you learn how to solve a differential equation using a power series. Power series, again series, right, will have these aspects of geometric series, which is something similar here. Every time you take, this is the solution you assume, you take its derivative, look at the counter. You take the second derivative, it will shift to 2. Anyway, so now you have this issue, we have that issue, we have to shift stuff around. You are expected to know this when you are sitting in differential equations class. So shifting the counter is not now just one annoying problem that you have to memorize for the test and pass it. It's going to be like, you know, this is something that we just do like, I don't know, completing a square or adding 7 and 9 to 16. So please don't, and then there's the solution at the end. So this is all one problem. From red line all the way down to, and that's one of the introductory examples. So it's beautiful, right? It's not going to be a problem at all. It's very systematic. It's more of a nasty algebra and annoying arithmetic calculation than any high concept once you learn chapter 8 and chapter 9 from Calc2. And if you don't know these things, chapter 3 is just going to be impossible in differential equations. So that's why make sure you guys are learning these concepts, because you're going to need this stuff. So I'm going to go through this one more time of how and what happened here. And then we are going to wrap up geometric series, because that's it. You memorize this, and if you see that the counter doesn't match, execute the procedure. Done deal. We are starting with geometric series. This looks like the exponential stuff, right? Like 2 to the x or 1/2 to the x, so it's kind of exponential looking. If you see a series that looks like that, you will use geometric series. You immediately figure out what R is by looking at it, and then wherever it fits, you get convergence or divergence. In this case, convergence. Since it converged, we can find sum by using the formula A over 1 minus R. Now, that formula only works if your counter starts at 0. Your counter started at 2, therefore we have to shift the counter. You shift the counter simply by subtracting the number that is not 0 to 0. So we subtract 2 on both sides, and we get now k minus 2 is 0. Define this, whatever it is, to n, which gives you your substitution, and then use that substitution to bring this k into n as well, in the exponent. So now you have your counter shifted and your exponent changed into n's. Now whether it's k or n, it doesn't really matter. And now you have n plus 2, which means that your formula will still not work because it doesn't look exactly like this. You have to have a single k, in this case n. So we have to peel off these plus 2, and we remember our basic algebra equation where if you multiply these two with the same base, exponents add. So you technically we call it peel off. So peel off these two, there they are, and then 1 squared is 1, 2 squared is 4, times 3, 1/4 times 3 is 3/4. So this is how it actually looks like. Observe that R did not change, so it's still convergent with the same R. But A did change from 3 to 3/4, and then you execute the procedure, and you get to 3/2 as the sum. And done. So when geometric series converge, you have to find the sum. You have to be careful about the counter. If they are divergent, that means that terms add either to positive or negative infinity. We don't care which one. So we just say it's divergent, and obviously we know it's infinite answer, so we don't bother doing anything else. And that wraps up the first test. Now we're moving to the second test, which is the last thing for today. And it's called telescoping series. Telescoping series. And these creatures are actually not well defined in a textbook we currently use, but they do pop up. They have it, right? But it's not made into a big deal kind of separate testing. Larson book does give it its appropriate dues. So how does it look like? It's going to look like a summation of I think they use bn plus 1 minus bn in a textbook. Oh no, this textbook like k's. K plus 1 over k minus bk. It can start anywhere. It can start at 0, it can start at 1. This one will not have. By the way, the only shifting of the counter that you have is geometric series. The other 9 tests will not care. So shifting of the counter, if you want to make that note, wherever we did the shifting on the counter, that only works. That only needs to be done for geometric series. Don't worry about anything else. So geometric series are the only one that worry about shifting the counter. Now that you made that note, we go into telescoping series. So telescoping series you are going to recognize by having this subtraction between two sequences. Sequence bk plus 1 and bk. Now it doesn't have to be k plus 1, it could be k plus 2, k plus whatever, right? So I don't like that notation very much. I would rather see bk minus ak, let's say. But it is what it is. Now, what do we do? Well, this is a procedure which you are learning. It's a procedure. So let's take a look immediately at the example. Summation 1 to infinity 1 over n minus 1 over n plus 1. No, n plus 1 minus 1 over n. There we go. Good now. So what am I going to do? Well, what I'm going to do is I'm going to start plugging in values. 1, 2, 3, 4, and come up with as many of these as I need. So first value that I'm plugging in is 1. So I have 1 over 2 minus 1 over 1. Next term would be when k is equal to 2. So I'm going to write this as k equals 1. Next one is k equals to 2. So what do I get for k equals to 2? I get 1/3 minus 1/2. Then the next one, 1/4 minus 1/3. Then the next one, k equals to 4. 1/5 minus 1/4. Plus dot, 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 dot. And it's going to go forever. But now, we can take a look at what's happening on what we would call the tail end, and take the tail end to go to a certain value. Okay, I'm mixing up k's and n's. That's bad. These should be all k's. K plus 1 and k. And then you're plugging in k is equal to 1, k is equal to 2, k is equal to 3, k is equal to 4. The reason is, this is the only book I know that uses k's. I learned it with n's from Larson book, and I taught from all other books, they all use n. And then this book uses k, and that's why I'll constantly switch into n's. It's annoying, but yeah, we'll live. So what I'm going to do now is I'm going to compute few tail terms.
What?
Tail terms. Tail. Tail, like a dog tail, cat tail, tail. Meaning at the end. And I'm going to do that as a value n, not k, n, new value, being the last in a series, and then I'm going to send that n to infinity. So I'm technically kind of cheating, right? Because what I'm going to do is I'm going to take the this infinity, make it finite, and then send that to infinity. We cheated like that in improper integrals, right? When you had integral 1 to infinity, and then you said limit, you put b, you make it a finite, and then you send b to infinity, right? That's what we did for improper integrals. So now we're going to do exactly the same thing for this. I'm going to say the last term must look exactly like the original, except it will have this n, which is what I'm placing in instead of k, and then I'm going to send n to infinity. And now I'm going to, for the term before this one, so this is k equals n. Now I need k n minus 1. That's the term before, right? If this is the last term, k is equal to n, well, replace every k with n. And now you're replacing every k with n minus 1, which means it will be 1 over n minus 1 over n minus 1. Naturally, this term here would be k is n minus 2. Oh, you had enough, huh? For the third time. 1 over n minus 1 minus 1 over n minus 2. You will figure this out. It looks horrible, but it's a pattern. You will figure it out. It's set up. That's it. Now look what you can do. Positive 1/2, negative 1/2. Negative 1/3, positive 1/3. Negative 1/4, positive 1/4. They all canceled, and then this 1/5 will have its negative 1/5 in the next term. I'm not going to sit there and write all infinity of them, but the pattern is clear. A half found its pair, a third found its pair, a quarter found its pair, well, the fifth will find its pair, and so on. If you look at the tail end, same thing happens. Positive 1 over n, negative 1 over n. Positive n minus 1, negative 1 over n minus 1. Well, then this one will have to have its pair somewhere in there. Everything canceled. What's left? Minus 1 plus 1 over n plus 1. But that's the one we are sending to infinity. So all of this now is equal to negative 1 plus limit n goes to infinity of 1 over n plus 1. Converges to negative 1. We computed the sum directly. Awesome, right? Come on. Work with me.
Yeah, I get it.
Well, we do one or two more examples and then we're done. Because there's nothing else. This section is over. Yes. You're just stretching. All right, now I'm going to put one of these problems you can stretch doing it.
Question. So, with the pattern, would there ever be a case where all of them cancel out, in which case it would just diverge instead of converge?
No, it won't.
Always converge?
But they could diverge. They could diverge because the limit at the end doesn't work out. For instance, I can come up with x squared minus x.
Yeah.
So, sorry, k. The pen doesn't work anymore. You have Apple Pen with you?
That's a Microsoft Pencil.
So k squared minus k, let's say, right? When you take in, eventually it becomes n squared minus n. Both of these go to infinity. So, right?
And that would make it diverge.
Yes.
Would there always be a case of? Would there be a case that none of the numbers cancel out? Like not none, all of the numbers cancel out.
Mhm.
There'll always be one that.
I have a question. Will these telescopes do quite the same thing?
Converges by telescoping, yes.
It's just two functions being subtracted.
Well, let's say that's it. You know how awesome math is.
It's super awesome.
Look at this next example. It's going to be brilliant. I keep writing x's. Or do I need a minus there? I don't know. That's good. So does this look like something that we can do by telescoping series? No. It does. How do we transform this into something that we can do telescoping series with? Partial fraction decomposition. There you go. I know, love it, right? It's awesome. So now you have to use partial fraction decomposition procedure to separate this into 2. Then the minus will emerge in between, and then you unleash the telescoping procedure for it. This is how awesome this stuff is. By the way, if those windows stay open with the lights over here, more dragons will come in. There was something flying around. Yeah. I don't mind. I don't care. It's just I don't want to hear screaming. The world is listening. How's your partial fraction decomposition going?
Oh, it's just dandy. No, it would just be
I'm sorry? You can always interchange them, right? As long as the minus is on one of the terms. You need the minus on one of the terms, otherwise it's going to diverge. So if you end up with something plus something, then you will be adding them to infinity, right? So you need a minus sign, at least. Yeah. What happened? Constants outside of the sum? Yes. if it's a common constant.
Does it always has to be? Does it always have to be 1 over something? Like the left term has to be bigger than the right?
They can add to -7, right? Or +7. So partial fraction decomposition is done already, as you can see. I factor out k. I split into two linears. I do the setup, two linears. Common denominator. Compare the equations. A is equal to half, B is equal to negative half. And then we can factor out 1/2 from both terms in front of the sum. And just drag it out all the way to the end of the problem when we're done. So now we have to write the terms out. And that would be one minus 1/3, right? Plus 1/2 minus 1/4. Plus 1/3 minus 1/5. Plus 1/4 minus 1/6. Plus 1/5 minus 1/7. Plus 1/6 minus 1/8. Why am I writing so many terms? Because I have to. I don't have cancellation in adjacent parentheses. So the more I write, I will get the better sense of the pattern, where I cancel. So here is a negative third, and here is the positive third. And I have a quarter and a negative quarter. And a negative fifth and a fifth. Now, first time you score the parenthesis where both are canceled, technically you're done. Because after that, once you keep the parenthesis that cancels both, this 1/6 and 1/6, so 2 terms survive. And it should be common sense that 2 terms survive because these are 2 apart. So that will tell you how many terms survive. Now you don't know which ones they are until you actually do this, so you can't escape doing this. But you can at least have a sense of how many terms are surviving. Because these are 2 apart, 2 terms survive. The first example I did, they were 1 apart, and 1 term survived only. That was -1. Now, so all of this, we see that 1/6 also goes away, and then 1/7 and 1/8 obviously will cancel in here where the 3 dots are. Now if we set up the tail end, tail end has to behave the same way. So the last term is always k equals n, and then work it backwards. So substitute n's, so it's 1/n minus 1/n plus 2, and then this is k equals n minus 1, which means you are taking away 1 from each n. Then k is n minus 2, but you take away 1n. K equals n minus 3, go to the previous one, take away again 1n. And k equals n minus 4, go to the previous one, take off 1 of the n's. Cancel. Here's the parenthesis. I already hit the parenthesis that had 2 cancellations, which means everything else has to cancel. And we are left with limit n should go to infinity. Oh, we have 1/2 in front. 1/2 and you are left with 1 plus 1/2 minus 1 over n plus 1 minus 1 over n plus 2. Both of those will go to 0 when you plug in infinity in denominator, and you have 1/2 1 plus 1/2. That's 3/2 3/4. So that series will converge, right? Converge by telescoping. Converges by telescoping series, yes.
But why did you go from k equals n as one interim all the way back to n minus 4? Is that just to make it more accurate, or?
When you see that they are apart from each other, you will need at least 4 or 5 terms. Because you see, over here is the first time where both terms canceled. But this n minus 2 term happened here.
Okay.
If I didn't have enough of these, I wouldn't find it.
So you have to just keep going backwards until you find
Yeah.
2 that cancel.
I remember telescoping series very well from my Calc2 taking experience, because in a class we did the example with them being 1 apart, two examples of that, and then on the test they were 3 apart. So I did 4 terms and 4 terms, and I said this stuff doesn't cancel. A lot of numbers are staying behind, so I said it diverges. I barely passed that test because it was just not cool what was going on. It was terrible. I don't know how you do it. So you saw that when they are 2 apart, one was 1 over k, the other one was k plus 2 or k minus 2, doesn't matter which way. If they're 2 apart, look, I have 5 terms here. If they're 3 apart, you will need 7 terms, I think. So just try. The textbook, unfortunately, gives you only 8 examples to practice. This is why I said Larson, they have 20. Yep, you have 8 examples. No, I lied. Not 8. You have 8 on the first page and 6 on another, 14 examples. Okay, they gave you 14 examples in the textbook to practice. But some of these, as you can see in this textbook, are scary. If you have Larson, just practice from Larson's book. If you don't have it, buy it.
You can turn it on Larson homework instead.
You can turn Larson's homework. So these over here are all beautiful. Look at this one, 62. Right? When you send these things to infinity, they're going to be possibly infinity. You'll have to do this limit as a L'Hopital rule on a side, because you have infinity minus infinity. Right? Yeah, welcome to chapter 8. Over here in chapter 8, we bake cookies without fire. It's hot all the time. Okay? 400 degrees stuff. It's called hell, alright? I can paint a picture of brimstone and fire. If not, there you go. So these that have denominators, all of them, they go to 0 like this. That's not an issue. But when you run into these guys, that's infinity minus infinity, and that might work out, because if you pay attention in Calculus 1 class when you did L'Hopital's rule, you know that there is infinity minus infinity, and it depends on how the functions look like, whether the answer is infinity or 0 or 3/4, right? Because infinity minus infinity is the tricky business. So please review L'Hopital's rule, and you will have to use for 62 L'Hopital's rule to figure out the limit at the end. Now, as you flip the page in this textbook, I don't know. I mean, yeah, these are fine. Sure. Look at that one. It's completing the square, maybe. I don't know. Probably. You have these inverse tangents here. Very interesting problem. And then these two stay away, right? So there are certain problems you can practice to find. Also on YouTube, you can find more examples. You will see the example, you pause the video, you do it, and then play it to confirm your procedure, to confirm the result, and so on. And if you get stuck, play it until that position, and then you see what's done, pause the video, finish off the problem, and then watch it to see if it's correct, and so on. So you can use YouTube videos to actually learn how to do problems. But the bottom line is, guys, you must memorize for all the 10 tests. All of the 10 tests are either formula-based, like geometric, or procedure-based, like telescoping. And you have to memorize every single one of them, and you are memorizing the forms, just like integration. You see x e to the x, you know it by parts. You see x e to the x squared, you know it's u sub, right? Because you practiced, you learned it, right? The same thing here. You see something that's exponential looking, geometric, see the subtraction of two series, or the partial fraction decomposition, or factoring into partial fraction, or completing the square into something, right? Also going to be telescoping. So that ends this section, and now it's the lab time. Yay! Bye.